All right, good morning, everyone. Welcome to Instance 2 of Operator Fusion here at the OpenXLA DevLab 2025. I'll introduce myself and my co-presenter, Karthik. I'm Kai. Karthik is a genuine bona fide compiler engineer with a ton of experience on the team, and he represents the TPU compiler and will be giving the majority of this presentation. He has done his postdoc at Stanford, a PhD at Rice, and an MA at UT Austin, specializing in high-performance compilers, and has also written a distinguished paper about the technology. I'm sort of the opposite. I come from the startup world. I was an entrepreneur for about 10 years, building and leading companies, including one where I created a domain-specific language and a compiler and a runtime and an ML stack, all for cooking food. So if you're into that sort of thing, come ask me afterwards. I'll be happy to tell you about it. And I lead the GPU compiler team here at Google. Okay, so today we will talk about various fusion techniques for GPU and TPU, and in general. We'll see some example fusions illustrating these techniques, and then we'll talk about how you can specifically apply them to your workloads, your research, your development, whatever it is, including flags and JAX annotations. So let's first set the context here. I realize that this is a little bit out of date, but the curve continues, and even more so. But there's a study from OpenAI showing that there's a doubling of AI compute demand and need every 3.5 months, which is dramatically outpacing Moore's law. And so to keep this up, we as an industry, right, all the players in this space have designed and built and fielded domain-specific accelerators. And obviously there are GPUs from a few different vendors. Google makes a TPU as well. And there are other customized domain-specific processors for these problems. We've also, of course, scaled those out tremendously. So there are huge deployments of these different types of chips. And we have tuned and tailored the software stack above them to take advantage of these capabilities. OK, so in this discussion, we'll talk about GPUs a bit, and we'll spend probably the most time talking about TPUs, which are Google's solution to the domain-specific accelerator for training and inference. And we'll explain how we get the highest performance from that chip. Also, to put this in context, XLA is our solution that we've developed to program TPUs, because there really isn't any other way. And the JAX framework and TensorFlow before it, and also PyTorch, can produce outputs that funnel into XLA, as you may have seen in Robert's keynote this morning. And then XLA does all the necessary compilation and tuning and whatnot, and then it can pass down these compute graphs to different architectures for instantiation into instructions for each one of those. OK, let's move on a bit, and let's talk about GPU first. So like on the TPU, fusions are a powerful technique in order to reduce the amount of HBM use and bus utilization. Really important. You'll hear in this presentation about all the ways in which fusion is really useful, but in its absolute essence, it's really this. We find that popular workloads these days tend to be memory bound, and there's compute to spare. Particularly, this is true of GPU, but really for every accelerator. So the more that you can pack into the available compute capacity of that chip, the better off you are, because you're not round-tripping memory to HBM, for example, amongst other things. So we also try to take best use of the cache, or really memory hierarchy generally, on both TPU and GPU. And on GPU specifically, we have a couple different ways to do that. So I'm going to set the context here. Probably most of you already know this, because the code's been open source for many years, and you can take a look at OpenXLA. But I'll just provide an overview of a few ways that we execute those fusions. We materialize them, really, manifest them. And then we'll go into the specifics of how we do it on TPU with Karthik. OK, so really, really briefly, we can lower operations on GPU via MLIR, where we do it explicitly. For gems and other sorts of patterns that are really suitable, we use OpenAI Triton to do codegen at a block level. That was added a few years back, and it's been very successful. And then we also have specialized, like domain-specific ways, including cuDNN, which is, of course, very GPU-specific, for convolutions, and now gems and some more sophisticated operations too. So again, at the high level with fusion, how do we do it and how do we decide to do it? It's true on GPU and TPU, but we do it in slightly different ways. But generally, we look for optimization opportunities. Sometimes they're called hero operations. And we will try to grab pieces of the graph, the compute graph, and then pull them in up until and we do this iteratively, up until the point where it is no longer profitable to do so. That's basically the TLDR. And we determine that profitability based on cost models. We have different kinds of cost models for the different chips and different techniques. And this is a NP complete problem, sorry, mistake there. This is a pretty good approximation in that, confronting that challenge of how difficult this is. Okay, furthermore, a technique that we use exclusively on GPU is that we also auto-tune, because there are some things that are not accurately cost modelable and are not deterministic. And so we allow different candidate fusions to race against each other, and whichever one is actually faster on the real hardware is what we select. So that's a pretty GPU-specific thing, but a kind of a general solution we can use in different places. Okay. Again, GPU-specific, we can use MLIR because it's a pretty mature and industry standard stack at this point, actually born here at Google, for those who didn't know. And it's a way for us to implement any kind of fusion that's, let's say, not served better by a more specific or specialized solution. And there are some certain cases, I mean, where this is actually better. So general pointwise operations, certain kinds of reductions and nested fusions, as well as small matrix multiplies, where it's just not worth it to use the other systems. So there's some places where MLIR is still king. Okay, cuDNN is a specialized solution, and we use it convolutions are exclusively manifested with cuDNN. And that's because we don't have a different way to do that at this time. And it's the best, right? It's an industry standard and widely used. It is also now capable of taking subgraphs for gem fusions. So cuDNN's capabilities have expanded significantly, and it can handle those as well as more sophisticated operations. And I'd like to say a big thank you to NVIDIA, a major contributor to OpenXLA, for developing these capabilities, particularly around convolutions and some other things that cuDNN can do. And then finally, we have Triton, again, OpenAI Triton, which we introduced a few years back. And we brought it in to explore how can we go faster with, in particular, mixed input type gems. But we took it from that, where it was very successful, and expanded in line with what I described before, trying to fuse more and more things into the inputs of these gems initially, and now we can do much more, up until the point where it was no longer profitable. And it turns out we could fuse slices, concatenations, transposes, type conversions, of course, and a few other things onto both the inputs and in some cases the output. And that has produced tremendous speedups on GPU, allowing some of our first-party workloads to get many times, I think 5.5 times faster was one achievement from a few years back. Okay, let's see, I'll just move along here. Now, we're going to transition into the TPU. I realized from the last time we gave this talk that not everyone has as much familiarity with the TPU as a platform. So it's probably worth saying it's quite different than a GPU. It is a small number of core, straight line, high performance execution machine. And in order to get the most value from a TPU, you have to, well, the compiler has to, fill in all of those instruction opportunities, let's say, right? You want to make maximum use of the hardware. That's true on any chip. Maximum use of the hardware over time to make to use the highest amount of capacity and the shortest execution. I realize that's very general, but the key difference is that we do it explicitly in XLA rather than implicitly as a function of the, let's say, CUDA runtime and whatnot in GPU, where there's sort of a mix. The compiler makes lots of well-informed guesses, and then at runtime, CUDA runs it. On the TPU, there is no such runtime, and everything is explicitly determined ahead of time by the compiler. So that makes fusions such a powerful technique for extracting performance from a TPU, and so vital to using the chip well. That's what I'll say for setup, and I'll pass it over to Karthik.
Yeah.
Thank
Yeah.
you.
Thanks, Kai, for that. So as Kai mentioned, so it's like the main difference between GPU and TPU is on the GPU side, you don't have scheduling control and you don't have memory placement. Whereas on the TPU side, we might have lesser number of threads, which are all in lockstep, but the compiler has explicit scheduling control. So it's like on the GPU side, you don't know when a warp is scheduled on which SM and at what time. Whereas on the TPU side, you know exactly when the 8K threads are running and where the memory is sitting. Sorry. So with that, like, let me give a bit more description of the tensor core side of the TPU so that the fusion techniques become much more malleable to understand. So and specifically, I'm talking only about the tensor core, not the sparse core. The sparse core is more of the random access core that's present on the tensor processing units. Very good for random access memory operations like embedding and stuff. Whereas the tensor core is more good for dense operations, matrix multiplication, transpose, vector operations like add, multiply, tanh, EUP operations, so on. So in this sort of schematic, we have like sort of two green boxes and the blue boxes. The green boxes are the memory units. So you have like a slow HBM and a fast vector memory. And the HBM is similar to your global memory on GPUs. And the vector memory is similar to the L2 cache that's available across all some SMs, right? Or per SM. On the blue boxes, they are co-processors, and specifically the one that I want you to focus on is the matrix multiply unit. So this is sort of the performance powerhouse of the TPUs. So because it is able to do like tiles of 128 by 128 multiplication, and it does it really fast. And so ideally, if I want to extract the maximum throughput from the TPU, I better produce a schedule that's filled with only MXU operations, right? So that would indicate that I am not seeing any memory traffic in the critical path. I'm not seeing any BPU operations or transposers on the critical path, all filled with MXU operations, that is the matmul operations. And that's how I'll get my maximum throughput from the TPU. And to do that, what do you do? To do that, we do fuse, and fuse. So we fuse ops so that I can hide the HBM to VMEM latency. And we fuse ops so that some of the ops can be working on the VPU while the other op can be working on the MXU. So fusion is a key, as Kai mentioned, it's one of the strongest features to actually get maximum throughput from the TPUs. Sometimes we fuse to reduce HBM footprints. Does anybody know of an instance where you want to reduce your global memory usage? Let's say related to transformers. The softmax layer, right? The softmax layer scales in n square, where n is the sequence length. And you really don't want to produce this result in your global memory because 6 GB or 8 GB or 32 GB can't like fit in for large sequence length. And that's where you want to fuse that softmax attention operation into the subsequent ainsum, which is the projection onto V in a transformer layer. So that's how you use fusion in order to also make your models fit effectively in the HBM. Now, the other way to go about it is you shard it across multiple chips, but that's bad because going off chip is always worse than staying on chip. So fusion is the key metric or the key optimization that helps you achieve high performance on TPUs. Just a few slides on 101 just to get everybody on the same page. So what's fusion? It's a technique which basically fuses two iteration domains such that you don't invert the dependence direction vectors. So let's say you have two ops that are in iteration spaces I1 and I2. You come up with a joined iteration space I such that you do both operations. And if there is a producer and consumer relationship between the two ops, you make sure that the result produced by the first op is consumed immediately by the second op. So here's an example to give more details. So there is an add consumed by a convolution, which is consumed by another addition operation. And let's assume that these two input 0 and 1 are fed to the add. And so basically the cardinality of the add is basically the size of that tensor. So let's assume that's n. Now, if you go to the con, for simplicity, let's assume it's a dot. Then the amount of work you're doing consuming the result of the add with the input 2 is an n cubed operation. And then you go to the next add, which is again an O of n operation in terms of the size of the tensor. So you have sandwiched between 2 of n operations and n cubed operation, and the adds use the vector unit because they're element-wise operations, and the dot uses the MXU unit. Now, if I were to schedule it just like this, my critical path would look like do the add, write the result to HBM, get it back for the con, do it on the MXU, write it out, and get it back again for the add. And that's bad because the one thing that I mentioned before was that we want to have a critical path which is filled with only MXU operations because that's the best way to get performance. So how do I hide that? I fuse all of them into this green box and make the con the lead operation. That is, the con's iteration space drives the work in this particular box. So in each iteration, the con decides what the add should produce and what this add should consume. And then by using sort of typical compiler techniques like software pipelining, which Sharad mentioned yesterday, you can hide the add work behind the MXU work in the convolution and achieve the goal, which is a critical path filled with MXU operations. So just to keep it self-contained, here's like the HLO representation. Again, it is like it's not fully syntactically correct, but what you see is a fusion primitive that takes the inputs, and then there is a kind specified to it. I'll come to that in a couple of slides. It takes some input, produces an output, and the composition of operations in the fusion are represented in the called computation. So that's how a fusion is represented. Now, this fusion is then lowered, that is, you generate machine code for it. And as I talked about, there are two things that you do. You pipeline, so which is basically you find the right tile size that the con should work on so that you can hide completely the HBM to VMEM latency while you are working on the sort of the subsequent tile or the prior tile in the VPU and the MXU. And once you get the tiling right, then within each tile, again, the tensor is like, these tiles are substantially big, right? So you want to unroll some of the work within the tile so that you can overlap the vector operations with the MXU operations. So you want to achieve both type of overlap in order to achieve the full performance. And this is where Triton sort of championed, right? Because it can find the really good tile sizes given a composition of operations. And even our compiler does that too. As Kai also mentioned that, so with fusions, the important thing is to reduce the overhead of the communication to HBM, maximize your task parallelism, and also reduce the HBM footprint. So the fusion infrastructure, you can like, it's a triad. It consists of a representation, policy, and the mechanisms. The mechanisms are wide, but we'll not touch upon all of them. Around four or five of them, and then we can discuss more later. So in the representation side, I talked about the kind primitive that was there in, or the kind field that was there in the fusion primitive, and there are three types of kinds that are important: the K output, K loop, and K custom. A fusion that's of type K loop means it's a composition of only vector operations. And crudely, the idea is a single loop harness can be used to lower all the operations present in that composition. So that's how they came up with K loop. So compiler folks are very bad at naming. So that's K loop. K output is a fusion that is a composition of operations where the convolution is present. Because we want to tell, or at least give the notion that the moment you see the kind, you're able to tell, hey, there is a convolution, and that's the lead operation that determines the whole iteration domain of all the ops present in the fusion. So that's why they came up with the name K output. But yeah, that's the name. So, and then K custom is much more intuitive. It's like when you have a Palace kernel that's fused with some of these loop and output fusions, then you call it K custom. And in those cases, in K custom, The lead is not exactly determined as easily by just looking at the op. It's more the lowering goes and then either selects one of the KL output or the Palace kernel to lead the iteration space. Now, how does the compiler go about implementing this fusion infrastructure? So it has a very, it's based on this policy. And in this policy, it's similar to GPUs. You have a priority queue that decides what fusion decisions are good over the others. And then the compiler picks one by one off this queue and then starts fusing things. Now, in order to determine what's a good decision, there is a good cost model. It's quick and dirty because you can't typically know the exact cost of running an op until you actually run the op. So at compile time, you make some assumptions, heuristics, and that cost model, in this case, the TPU compiler cost model, kind of looks at an op and decides how much MXU, VPU cycles that it needs to lower the op, and then constructs a pseudo fusion node, and then also asks the same question, what's the cost of this fusion? And then determines whether the fusion decision is good or not. So the tile size, again, is under the control of the compiler. So it kind of can anticipate the memory overhead because it knows the tile size given an HLO. Then once it knows the tile size, it also knows the individual ops, what they map to. So there's some crude approximations there. But overall, a good heuristic to derive the fusion decisions. And as I said, it's an NP complete problem without there is no way to kind of exhaustively enumerate all fusion decisions and then evaluate what's the best. But some heuristics in this policy are much more like intuitive. So for example, broadcast will always be fused. Anyone wants to venture a guess why broadcast should always be fused? Data transfer, exactly, because broadcast is, you're not materializing anything, you're just like, making copies out, and therefore, and the broadcast output is strictly larger than the broadcast input. So if I don't fuse it, I'm clearly going to move the broadcast output to HBM, and that will be in the critical path, which is a bad thing. Fused with a subsequent op. The broadcast as a producer should be fused to a consumer so that the broadcast output is not materialized in HBM. Then there are some, then there are scenarios where you have a dot that's consumed by multiple operations. Now, clearly, you don't want to fuse that dot to each of its consumer because that's simply increasing the amount of compute intensity for me, and so you clearly don't do it. But now, in some cases, it might be necessary that I fuse, again, softmax and other cases. Let's assume that the softmax actually had the Q at K fused into it. Now the question is, would you fuse that back into the subsequent at V projection? You would, because that will help save memory. And so when memory savings are critical, you need to violate some of these heuristics. So here's an example. This is how I think Kelvin was here. Here he sort of described XProf yesterday, and there I think you touched upon how these fusion nodes look like and so on. We are just doing a brief run through of the same. So this full box is one fusion node. The lead op is colored blue, which is the convolution, and the convolution is taking a kernel, which is another loop fusion, and it's taking an activation, which is just a bitcast, which is kind of a no op, and that's the K output fusion. Now I have to kind of justify why this fusion was good, right? So now how do I go about doing it? I do a bundle analysis. So bundles here represent sort of the code that was generated onto the TPU, generated for the TPU. And in this graph, you see the bundles on the horizontal axis. You can think of instructions. And on the vertical axis, it's like an occupancy metric for different co-processors. So if the VPU is used, the vload, vstores are used, or if the MXU is used, you get a dot on the vertical axis. And so across the bundles, you kind of get to know how your different co-processors are being used. In this case, the red line indicates MXU, the blue line indicates the VPU, the vector operation. Now, this is what I want all my ops to be. That is, I want a a red line through and through all the bundles at the maximum utilization factor, which tells me that the MXU is engaged in each and every instruction bundle. Now, this VPU also is, this also indicates that the VPU is in parallel with the MXU, and there are no sort of like blocks of time where only the MXU is used or only the VPU is used. Now, can anyone tell me why is there a blue line here, given this HLO op? The blue line indicates vector operations, VPU, which here is the vector operation. The maximum, exactly. The dynamic slice pad, everything is address arithmetic. So there's nothing about the VPU usage for them. And then only the maximum is the one that's using VPU, and that's also not used as much, right? Because it's O of n, and the dot is n cube. So that's why you see periodically the maximum is being done, but all the other time the MXU is being done, and our software pipelining plus unrolling is working well for us. It's just address arithmetic, so scalar operations to determine where exactly you would fetch, right? You're saying dynamically slice an input tensor and fetch from there.
Why is it MXU users?
It's not an MXU user.
The red lines were not.
The red line is MXU usage, but from the convolution, not from the dynamic slice. This is showing the whole output fusion. The red line effectively is convolution, the blue line is maximum. Yeah, so we looked at what fusions are, some policy, not the entire thing, obviously. And then now we'll go to the different techniques. They act separately, might be a description. I can't tell you like how's the linking, right? Like that will be telling you what's the layout of the TPU chip. So I can't tell you that. The fusion mechanisms are much more interesting because this is where we slightly deviate from the GPU. We do much more different things because of the ability of the TPU compiler to control schedule and memory placements and the lockstep fashion of these 8K threads, 8K or more threads. And I'll go through multiple of these mechanisms. So we kind of use compute with collectives. And collectives are basically operations which are like basically gathering or scattering data across multiple chips. And they use the network infrastructure in order to do this. So we also do like these novel continuation-based fusions where you fuse an op, but you don't guarantee completion of the op within that particular fusion execution. And effectively, it maintains a continuation state that gets plumbed to the subsequent fusion and where it gets completed. And let's look at this one in particular. So overall, kind of I describe it as fusions are in a spectrum where you go from shallow fusions to deep fusions. Shallow fusions are fusions of independent operations. Deep fusions are more producer-consumer, where you're fusing dependent operations together. And shallow fusions would be your like sort of ICI plus, sorry for the ICI. ICI is like your sort of network infrastructure, and ICI versus sort of MXU usage can be overlapped, or your MXU and ALU overlap. So the first technique, shallow fusions, in shallow fusions. So in shallow fusions, you can look at a typical fusion structure of this format, where you have compute, the lead compute on one side, and you have a data independent operation X that's fused in, but it's not guaranteed to complete within the execution of this whole fusion node. And the idea here is, if I don't perturb my main compute, then in all the stalls that might occur because of waiting for MXU, waiting for VPU, or waiting for memory, I can slide in another operation X and do some work for it and update its continuation state. So if X is a collective, let's say I'm doing all gather, which is I'm gathering this tensor across like thousands of chips. Now, most of the time I wait in such an operation is waiting for data to move on the network bus. So when I'm doing that, the tensor core is idle, right? So here what we say is, let's do the main work, and every so often we go and check what we need to do for X. Has the data for X arrived? If so, then take the next step of communicating. Else, just go ahead with the main compute. Now, in V5 onwards, I think, are there TPU users here? Oh, okay. So some of them. Good. So, and hopefully at the end, all of them are, right? Like having. So if X is a collective, and you might have seen these fusions, I'll show you an example soon. So X is a collective, like an all gather, all reduce, and it has a state. It's basically a bunch of scalar instructions that maintain the state, and then that gets plumbed to multiple fusions and gets completed. Here's the example, and as promised, not to make it a presentation, but some amount of tutorial. So here are the flags that help you control this particular fusion. So the fusion node looks like that. You can see that this is completely data independent. The all reduce is the collective reading from parameter to finishing up and producing a result in the tuple. In this case, we needed only one step because the all reduce was pretty small. So you didn't need to fuse it across multiple fusions and maintain state and so on. Instead, you just did it in one shot in this particular fusion. And the flags that can control is this. For example, if you say XLA TPU enable async collective fusion fuse all reduce equal to false, then it won't fuse that particular fusion in that manner. Now, ideally, all reduce is in the HLO, everything is static, and the sort of the time taken to push something on the network bus on these optical channels. So why wouldn't I always do this? So why would I need a flag to sort of control the all reduce? Yeah, okay, I'll stop making it more like question answer. So the thing is about what does the all reduce end up being, right? It becomes like an asynchronous operation that was initiated way ahead of where it needs to be placed and then finished at a later time. This increases the live range of the tensors that the all reduce consumes and then produces. So that puts extreme HBM pressure, and therefore you need sometimes when you need to nudge the compiler to say that don't think of performance, think of memory, because I'm trying to fit the model rather than run the model end-to-end latency perfect. We need these flags to turn and off, and and that's why you have, like, say, even fuse all gather and fuse with mosaic custom calls too. Sorry, default for all gather is on, all reduce is off. You can get into the details of it because it's a cost model which is HBM aware. It kind of like as you're making this collective fuse across fusions, you're increasing the HBM pressure. So the cost model is no longer about thinking about how many cycles of perturbation occurred across the compute, but it's also thinking about how much I'm increasing the HBM pressure. So it's a pretty good cost model. It's a more sophisticated one. Now, it still looks like an all reduced, but you will see a state variables plumbed through the fusion. They go from the input directly to the output in the fusion. So it's not a great syntactic structure, but right now, okay. So two things. This is because this is fully available to you when you look at the XProf. So what will happen is the all reduced looks like the same way, but there are extra scalar variables that kind of denote the automaton for the continuation of the collective that are plumbed as inputs to the fusion and directly go to the output. And in the backend config of the collective, it will be indicated which variables to look up for the collective state.
But it's also like statically known, right? Like it's not like
No, it's not statically known, right? Because you don't know how your chips arrive, different cores arrive at different points in the collective. So one core could be a straggler, and then it can hit the compute late, this particular fusion late, whereas the other one can hit it earlier. And so
in the sense that like different workers may hit it differently, or
yeah, they will hit the collective differently, and so it might not be like I mean, I'm assuming that's what you're aiming for. That is, it's like most of these calculations in terms of latency and bandwidth usage of the collective is completely static because you know the tensor size, but you cannot predict still the timing because of this, stragglers in terms of how the chips arrive. Exactly, it does. It does. That's why I said by default it is off. One of the reasons is when you need to do ALU work, you also eat into your like cache to hold the sort of the tensor needed on which you need to do the VPU operations on, which is the whatever is the sharded all reduced size. And because of that, your main operation compute could get perturbed because the tile size with which you are going for is no longer the most performant tile size because there is another tile for the all reduced competing for the same VMAP. Hence, it's like only if the user really wants it, it's available. Okay, now actually one of my favorite features, which is like fusing where X is a compute. Yeah. Okay. So like we have two fusions here. One is the white box fusion, and the other one is the pink box fusion, and both are K output fusions. They look great. We ran the bundle analysis. Individually, the fusions are good. So, what can I do better? And the idea is, what if I take all the VPU operations that were stuck after the convolution, and then I fuse it to the parallel convolution, that is the other convolution that was not data dependent on these two. And here it ends up that this is a much better technique than keeping what was there before. And the reason is as follows. So now let's look at only the left-hand side, how it changed. The left-hand side is now the pink box with the original convolution, but new VPU operations added which are parallel. So if I look at the original convolution, it had the same red line and the blue line, red line MXU, blue line VPU. Then I added this new loop fusion. When I ran it standalone, the usage was like this VPU operation because there are only VPU operations to be done in that max and tanh. But when I combine them in parallel, it looks like nothing changed. I still take the same number of bundles or I did the same fusion in the same amount of time. And what exactly happened was this blue line was not maxing the VPU usage. And it was also not a memory bound op. That is, there were not many HBM transfers. So whatever HBM transfers and VPU needed for this cloud, pink cloud of operations was perfectly hidden with the blue line of the convolution. So the MXU remained the same way. And the blue line just bumped up a little bit. We increased the intensity of the VPU operations, but overall we kept the execution time of the left-hand side fusion the same. So great. So where is our performance improvement coming from? The performance improvement is coming from the right-hand side convolution, which is now free of the VPU operations. Because it was free, it was able to go for a better tile size because there's no VMEM there's no VMEM competition to hold the VPU footprint. And because of that, it chose a different tile size, was able to maximize the MXU usage. The yellow line is the right side convolution fusion, and the MXU usage is fantastic, basically, which is like continuously engaged. And that's where we get the 4% improvement on one of the TPU platforms. So this is the parallel compute shallow fusions, the second technique that we looked at. And the flags that you can use to control this is enable advanced multi-output fusion and enable multi-output fusion. Advanced gives you the opportunity to build with compute with continuations, just like collectives with continuations. Say you don't want to finish a particular set of VPU operations in one fusion, then you want to plumb it across other fusions, then that flag helps you. In the interest of time, I'll just skip this. This is similar to another collective fusion. But I'll go to something a little bit more interesting, which is dot fusions.
Can I interject something because we didn't say it earlier? On the TPU, convolutions and dots are treated the same, right? Because a convolution of one-by-one filter is degenerate. It's basically a dot. So that's why you see the terms used interchangeably. Yeah,
sorry about that. Yeah. You can think, convolutions are two-level matmuls. Yeah, so what I have in this collab is just like a simple transformer layer, a multi-head attention, which does Q at K, softmax, and then at V. And then followed by like a simple MLP layer with like FF1, FF2, sandwich between them is the ReLU operation. So now, when I run this, one of the things you can ask is like, can I fuse the ensemble? That is, can I fuse multiple dots, MXU operations together, and still there is opportunity for improvement? And the answer is yes. So for example, if I run this with this flag called dot dot fusion true, I mean, XProf is one of the best things that I've used. And so if you learn how to maneuver through it, it's one of the best for performance analysis. So I know where to go in this case. So I'm going a little bit faster, but this is the fusion that was produced where I was able to fuse the ensemble weights into the subsequent attribute projection. And you can see the add and the maximum also coming in. Now, on the other hand, I don't want to fuse that. I turn it off false, run the same thing. I'll increase the graph width because I need to see both. So you can see the same convolution, add maximum cutoff, and no nesting of that into the subsequent fusion. So these are two independent fusion nodes as opposed to the other case where they were fused. And where exactly is the opportunity? Yeah, it's basically I hacked in so that I can show in. So there are some random operations I threw in the middle so that yeah. It's not a 101. Yeah. There is also a random v plus where v is values are scaled by the square of v. I just needed the fusion, so yeah. So you can see that. So the advantage comes from, as I think Kai also mentioned a little bit before, is that there are gaps in terms of, even when you're using the MXU at full throttle, there are gaps in the MXU usage because of waiting for VPU operations to finish, because of the size of the sequence length and so on, or waiting for communication to finish. And in those places, you can introduce like sort of, if you sort of pipeline and unroll enough, you can issue the MXU of the producer dot in those sort of holes. Yeah, and then the flags that help you control this is dot dot fusion, multi-level dot dot fusion, and so on. You can have more than two, so you can go as deep as you feel is necessary, right? Like if the structure of your dots are. Again, so when you fuse, you're increasing live range. HBM pressure is one metric. Now, overall, like, you know, if you don't get the holes right, you might end up with worse performance because we are not able to actually run the op and we are relying on heuristics, NP complete. So that's why the tile with which this window was could have been lowered as in isolation versus the tile of this in isolation. I don't know that exact tile numbers because I don't exhaustively enumerate that during fusion decisions. I do it only when I am generating the low-level code. So the fusion cost model is slightly different from the actual lowering tile model, and therefore, because of that, my fusion decisions are at the mercy of this sort of tiling scheme. Maybe I answered it. Well, anyway, so the idea is like the fusion cost model is different from the cost model that helps you actually produce the low level code. And then, yeah. So, and this is softmax fusion, as you might have heard in literature, it's flash attention. So yeah, this is simple fusion that happens by default in the compiler. Of course, because of the nature of the layer, this can change. And then these fusions look way different. But the flags that you can use is prefuse self-attention or RWB fusion. You can turn them on and off to get some of these fusions. Okay, and then so till now it was about flags, but as you saw how Robert laid out his vision, it's also about giving control back to the JAX user. And so at the JAX level, if you have like a particular bunch of ops that you want to make sure that they fuse, then you use the must fuse attribute and with the region ID. And the compiler will say that everything with the same region ID will get fused together. And then this is not yet in the JAX version, which is in public domain. It's there only internally, but soon we hope to put it out into the public JAX Lab release. So you would want to attribute like different clusters with different fusion capabilities, right? So you want to say, I want to fuse ABC but I also want to must fuse PQR, but into different fusions. So region ID is a way of identifying these clusters of fusions. It's being discussed for the GPU side as well, and it is called JAX.fused. And then you write the sort of the function or the context with the ops. But again, it's not public domain yet. And so again, with the JAX custom call, it's in the compiler again. It's okay. So compiler is free to fuse how many ever ops within the custom call. We inline some of these calls, and so to the compiler, it looks like 10 separate operations, and then again, it will use its cost model to say which are good fusions, which are not. But then, if you really want to make sure it is a single fusion or fail if the compiler can't produce the fusion, then you will use the must fuse. Yeah, and with that, I think we are at the end of the presentation. Happy to take any more questions. I'll keep this one rolling for the questions as well, right? Yes. Go ahead.
So you mentioned that somehow we decide a tile size such that the loading of next tile is overlapped with the compute of current tile. Who makes that decision, and what the tile size should be so that this loading becomes overlapped? Does XLA do it? Does Titan do it? Backend do it? Who actually makes
the TPU compiler does it. XLA. So XLA is like, I guess, then comes down to one level to a TPU or platform specific portion of the backend. The platform specific portions do it. Even for GPU, I guess.
There are different techniques on GPU for that kind of pipelining. And depending on whether you just let us code generate via, let's say, Triton IR, there are certain techniques. If you write it explicitly using Palace, by way of Mosaic GPU, you have more control, but it's a different path. So yes. But in this case, we're talking automatic on TPU.
Yeah, TPU is automatic. Yes.
You mentioned at one place where already you not prefer to overlap the already because of memory pressure.
Yeah.
So my question is that in GPU there are some norms where you can control the size of all reducers to make it smaller, shorter. So basically, I was just wondering, all those thresholds are kind of manually tuned.
Yes.
So I was wondering, on GPU, do you also have something like that, or is there any plans of making them kind of automated in the cost model as well?
No, on the TPU side, it's the same. So if you want to use the short emitter, that is the again, as you said, the all reduce, depending upon which axis you're doing the reduce, which is the sharding you applied, you can completely control what's the all reduce footprint. And then, so you have flags for the all reduce. I can pull it up. I think they're public domain as well. So you can control those flags and the flag I mentioned in order to get the fusion that you want. But then again, this is highly dependent on the sharding that you applied, right? So, which you can control again with Shardy, or there are global flags that help you control the compilers, auto-determined sharding as well. So you can, in short, you can control how big the all reduce is, how you map it, what is the algorithm you use to implement it, and then correspondingly what fusions you choose to do with that all reduce, all controllable on the TPU side.
TPU yes, GPU no, I think is the short answer, right?
Yeah, short answer is yes. So, but again, it's not just about the platform. You want to fix your execution options and your compilation environment, which includes most of these flags. So even if you change one, then you're not guaranteed the same.
And the reason that even holding all those things constant on GPU, it's not deterministic, is because we rely on auto-tuning. And auto-tuning naturally has sources of noise, thermal power, all kinds of stuff. And you can switch it off if you wish to. You can force it to use auto-tuning cache results. There's some ways you can make the thing deterministic. And some of our customers need this.
If you turn the auto-tuner off, does that affect the performance?
Absolutely. But what you could do is something like an exhaustive auto-tuning pass, have everything saved to a cache, and then all subsequent compilations can pull from that cache and just say, just trust it. And that's, like I said, there's some customers that do this.
So there are certain flags which help with this optimization called prefetching tensors. So if you recognize that it's a weight, and you know that it's not going to be like, the next layer weights can be prefetched in the previous layer, because if you have enough VMem space available for you, and so you don't have to tile them. So you have the whole weight tensor actually for the next of the MLP layer available at the time you do the dense matplotlib. If you don't, we have techniques to sort of slice it, and then get portions and then work on it so that you avoid the prologue overhead of fetching the first tile and stuff like that. Yes, absolutely. So it's like we play with the layouts. I think all the sort of the people who are working in the last 10% performance play with layouts, fusion, scheduling, everything as one big sort of pool. Yeah, but you also have to think, right? It's optimal layout for the weight, which will help. Will you get the best tile size and performance from the feed forward dense matmo? And then you also have to think about, like, sort of how you can shard it, such an optimal layout, because it's not only about one. Because if you look at even inference workloads, they are not served on one chip; they are served on X by X chips. Forget training. Training is even much larger. So you'll have to work through the global sharding, the local tile size, and then can you prefetch it or not, and all that. And again, if you drop quantize to it, then most of it becomes simpler, smaller footprints.
Okay, thank you so much.